All right, so today we're going to talk about a new type of reaction that we like to call SN2, and so that's sort of an acronym for substitution, meaning that we're going to take one thing, substitute it out for another. Nucleophilic, the mechanism that we're going to do to substitute these things is by the use of a nucleophile or nucleophilic mechanism, and the two sort of stands for bimolecular, and what that means is that we're going to have two specific species that are present in the rate determining step. So let's talk about what those are. For a typical SN2 style reaction, we have to have some kind of a nucleophile, so we'll abbreviate that as NUC. These nucleophiles will have at least a lone pair of electrons on them, if not a full-on negative charge. So this nucleophile is what we like to think of as going out to attack a nucleus, right? It wants to get at a nucleus. So what nucleus is it going to attack? Well, we need to have another partner in this reaction, and that can look something like this. Okay, so that hopefully looks pretty familiar, but you might be asking yourself, what is Lg? No, it's not some element that you didn't know about before now. Lg is just an abbreviation for leaving group. And the leaving group is going to do exactly what its name suggests, is it is going to get out and leave as a part of this mechanism. So that can be a little guiding clue. The rest of this molecule, you could call it a substrate, but we also like to call this the electrophile. Because this is what's going to be attacked by our nucleophile. So the nucleophile wants to grab a nucleus. The electrophile wants some of the electrons that the nucleophile has. So they kind of go hand in hand. So where exactly on this are we going to attack is a question that you might ask. And there's a couple of different ways to think about that. So if the leaving group we know has to leave in this reaction, we know we're going to have to break this bond. So that means that we're going to have to attack the carbon that's immediately adjacent to it. So that's one way to think about it. The other way to think about it is that based on the identity of the leaving group, which we'll talk about more in the future, these are often pretty electronegative atoms or functional groups, which means they're going to be drawing a lot of electron density to themselves, and we'll have a dipole that looks quite a bit like that, which means that that carbon has a substantial partial positive charge to it. And so we like to call that carbon that's immediately attached to the leaving group the electrophilic carbon. So now that we've got all those pieces and parts, we can actually make this reaction happen. So the nucleophile is going to reach out and attack at that carbon center, and our leaving group is going to leave. So with our arrow pushing, we always want to start at a pair of electrons or a negative charge. And we're going to attack this carbon atom kind of from the opposite side of the leaving group. So this is what we call the backside attack. Because it comes from the backside or behind the leaving group. And this is very important, and we have to do this orientation of the reaction based on the arrangement of the orbitals in our electrophile. So that said, we've attacked this carbon, and that means we're going to make a new nucleophile to carbon bond, but we have to break one so that we don't have 5 bonds to carbon, and so our leaving group is finally going to do its destiny and get out and leave. So what do the products of this reaction look like? Like I said, we made a new bond from the nucleophile to our carbon atom. All these hydrogens are still here, and the leaving group got out and left on its own. It's going to sit there as either a neutral species or also often a negatively charged ion. So if we were to talk about that rate determining step that I mentioned earlier, we could draw out a little diagram for what that looks like. At the highest energy point, or the transition state, we could draw a cartoon of what's happening that looks something like this. Where we have our carbon atom, we have our leaving group that's kind of on the way out, and we have our nucleophile that's on the way in, right? So we like to draw these as dotted lines to show that that bond is not fully made, but it's not fully broken either. So we would say that this bond is in the process of breaking. And this blue dotted bond is in the process of forming. So we'll talk a little bit more about what the lengths of those bonds means in a second, but the other part that I want to draw your attention to is here I've highlighted the nucleophile in blue. This will have a partial negative charge to it during this transition state. So that's one of the partners in this reaction. The other one is here's our electrophile, right, with the leaving group starting to break and starting to also obtain a partial negative charge to it. But this is the 2 different species that are required in our transition state, which means that the rate of the reaction is dependent on the concentration of both of these things in solution. So the other part to this transition state diagram is that the length of this bond that's forming and the length of the bond that is breaking are about equidistant. That is to say that the nucleophile is as far away from the carbon atom as the leaving group is. So what this tells us is that the nucleophile is coming in kind of at the same time that the leaving group is leaving, that all of this is happening all at once. And so what does that tell us? That tells us something about the mechanism, right? So we like to talk about this mechanism as a concerted mechanism. That means to say that it all happens all at once. So just like an orchestra plays all together in a concert, this happens in a concerted fashion. So it's just one step as I drew above. That's all there is to it. It happens all at once. So because of the concerted nature of this reaction, that has some implications for our stereochemistry. So let's look back at our original example. If we look at this, that has 3 hydrogens on it. We should know that that is not a chiral molecule or anything with stereochemistry. We don't have to worry about it for this specific example. But if it were, then we might have to pay attention to it. So notice how all of the hydrogens on this example, right, are all kind of pointed toward that side of the room, right? Some of them are sticking out, some are sticking back, but they're all pointed that direction. And then the nucleophile comes in, and at the end of the reaction, now all the hydrogens have been swept around and are pointed to the other side of the room, right? So when they're swept along like that, that has stereochemical implications. And the way that I like to think about this, especially this time of year, is kind of over here when we're starting. This is like, you know, oh, I know it's going to be a rainy day today. So I've got my umbrella. Beautiful cartoon umbrella there. And then sometimes the weather just really doesn't want to cooperate. On top of the rain, you get some wind. So the wind in this case is going to be like our nucleophile. And just when you don't want it to, it comes and gets under the backside of your umbrella, and then it kind of blows it out, right? I know I've had to throw away some umbrellas when this happens to me, because at the end of this reaction, your umbrella is going to look something like this. So there's my umbrella that's now been blown out, and probably a bunch of these support struts are totally broken, and now it's totally unusable. So if we think about this umbrella, the beautiful, lovely umbrella that's ready to go, this is the useful configuration of the umbrella. And then at the end of this reaction, we have an inverted umbrella, or an inversion of the original configuration. So what this means for our purposes is that we need to remember that SN2 always goes with inversion of configuration. That does not necessarily mean, however, that it goes with a change in R or S. So we'll talk about some of the strategies to address making sure that you're paying attention to the stereochemistry in some examples coming up next.